This video provides an overview or a summary of the content, the main content in the current chapter that deals with impulse and momentum. If you're seeing this video before you read the text material, then it will serve as a preview of the kinds of vocabulary you'll encounter, as well as a first look at some of the more important equations. If you're viewing this video after you've read all of the content in this chapter, it will serve as a helpful, I hope, review. This lecture is about impulse and this other thing called momentum. So let's begin with the discussion of impulse. An impulse is said to occur whenever one object strikes another. And that striking period, that contact period, the pushing period or pulling period, lasts a period of time, which we call the contact time. It's the amount of time that the force is in contact with the struck object. The impulse suffered by or experienced by the struck object is symbolized as I for impulse, and it's equal to the average of the force that was exerted on the struck object over that period of time t, times the period of time t. So it's the product of average force F bar times the contact time t. The units of impulse are the units of force, which are newtons, times the unit of time, standard unit second, Newton second. The Newton second then is the standard international unit for impulse. I show, or it is shown in the text portion of the textbook, that a Newton second unit is equivalent to a kilogram meter per second. And by the way, there is another quantity, a very important quantity, that is the companion to impulse that is discussed in this chapter. It's called momentum. The momentum of a single object is symbolized as lowercase p, doesn't remind you of anything, and p is equal to the product of the mass of the object times its velocity. Now, this is the equation you use when you're studying an object that's moving along a straight line, so that we can indicate its direction with a positive sign if it's moving to the right or upward, according to our velocity rules from way long ago, and negative if it's moving to the left or downward. The units of momentum, you can see, are the units of mass, which are kilograms, times the unit of velocity, meters per second. That matches this here. So we see that the units of impulse are the same as the units of momentum. Now, a very important equation, the most important equation, perhaps, in the first half of this chapter, is the so-called momentum-impulse equation, which states the following. Change in the momentum of an object equals the product of the average force that was acting on it times the contact time. A shorter version of this equation is shown here, replacing mv with the momentum later, unsubscripted, and mv naught, the later or earlier momentum, with the symbol p, subscript naught. So we have an alternative form of this basic equation here that you might want to use, probably won't. A shorter version of this equation is to represent the change in the momentum of the object as delta p. Right-hand side, no change. The shortest version of all four of these representations of the same idea is shown here, delta p equals I. The vast majority of the time, the equation you will put to use in your study of impulse and the corresponding change in momentum that the object experiences is this equation here. Now, let me describe to you the kinds of problems that you might encounter when you put to use this rule. But first, let me give a name to this idea here, in equation form represented in four different ways. This is called the momentum impulse theorem, or momentum impulse rule. The change in momentum of an object equals the impulse it experienced, the impulse it suffered. Well, there are ample examples of impulse versus change in momentum problems in the text, so we won't go over those here. My purpose, as I said at the outset, is to provide you an overview of what you're going to see in this chapter, or a summary of what you have seen if you're looking at this after having looked at the text. I show here two objects, perhaps lying on a tabletop, or two automobiles on a straight road. We're going to consider a one-dimensional problem in which the objects collide. Perhaps this one is chasing that one that's moving more slowly, and it bangs into that one. Or maybe the two objects are moving toward each other and about to suffer a head-on collision. We will then be speaking of a one-dimensional situation, 1D, in which the objects are moving on the same straight line before and after they collide. What I just state now is true without proving it, is that the total momentum of this system, this pair of objects, before collision occurs equals the total momentum afterward. And we're going to use uppercase P. That's a lowercase, lowercase, lower, lower, upper, 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 upper. Uppercase P will represent the sum of the two different momentums that our system of two particles has. The following is true. The initial total momentum, P naught, is a sum of the two initial momentums. For object 1, P1 naught, object 2, P2 naught. That's not a 10 and that's not a 20. It's P1, initial value naught, P2 naught. Well, the total momentum after the event, after the collision, is the sum of the two separate momentums, P1 and P2. Well, we come now to a conservation law, which I state without proof, it's proved in the text, that the total momentum of a system of two objects, or more, but we'll never discuss more than two objects in this chapter that collide, the total momentum after collision equals the total momentum before collision. Uppercase P equals uppercase P naught. These are the equations you put to use for a one-dimensional collision of two objects. Now, it's possible that you will encounter objects on a tabletop or on a plane, a horizontal plane, that collide, as is the case, for example, two billiard balls collide on a tabletop, suffer a glancing collision with each other, and move off in different angular directions compared to before. So here we'll be talking about 2D motion, two-dimensional motion, motion in a plane. In such a case, with the collision of our two objects, there will be the x component of the total momentum after collision and the initial value of the x component of the total momentum before collision. We likewise have the final y component of the total momentum equaling the initial value of the y component of the total momentum. This is the idea you'll put to use when you study two-dimensional collisions. And the last important thing that you need to know about the content in this chapter is that in our studies of one-dimensional motion, back here, there's a special type of collision, a rare sort of collision, in which the kinetic energy of the two objects afterward, add them up, is equal to the total kinetic energy before the collision occurred. Such a collision is said to be elastic, and we represent symbolically the fact that an elastic collision occurs by stating that the later total kinetic energy, K, will equal the initial total energy, K naught. Again, this case here will apply only to our one-dimensional collisions with the objects before and after on the same straight line. There are elastic collisions involving two-dimensional collisions, but the mathematics is too cumbersome to spend our time on. Well, I hope this will be helpful, or is helpful.